So this is the third video about second order differential equations. In the last video we looked at the more general type of differential equation here with this very familiar left hand side, but we started looking at being equal to not just 0 but equal to some function of x, and we did one example where that function of x happened to be a linear function and was in fact 4x, and we solved that one. But there was a point where we got to the stage where we were trying to choose a particular integral, and I just wrote one down without really explaining where it come from or how you would do it for other function of x's in the future. So the first part of this video is to go through the different functions of x you may come across in FP2 and what their associated particular integrals would be, and then to go through an example with a different function of x so we can see how to solve them with all this kind of particular integral stuff, this information shoved back in. Let's start by writing out a list then of all the functions of x you may come across in FP2 and what their particular integrals will be. So the first kind of function of x you may see would be just a constant, it's a number over here, something like a 3 or a minus 2 or 5 or something. If that's the case, the particular integral is just a constant, lambda. The idea is you work out what the lambda is by doing the method, we'll see that later. What other function of x happen to be linear? So like the 4x we saw last time, or maybe a 5 minus 5x, or maybe a 3x plus 1. It may have some constant terms. As long as the highest power is just an x, then it's still linear, and the particular integral was the same as we saw in the video, y is equal to lambda x plus mu. Again, here we work out what lambda mu are. Or maybe the function of x is a quadratic, so something like a 3x squared, or maybe a minus 4x squared, or maybe an x squared plus 3x. It doesn't matter again if it has lower powers, if it has constants in there, as long as the highest power is a square, that's a quadratic, and the particular integral would be lambda x squared plus mu x plus this weird little v thing called nu. Okay, what was something more interesting than like a trig function, like a sine or a cos? This is slightly different because you can have different kinds of sine functions. So you can have like sine 3x, or you can have something like sine of x, or you can have like cos of 4x. And what's important here is the number in front of the x. So if it's a sine of 3x, you'd be letting the particular integral be lambda sine 3x. And plus mu cos 3x, which is a bit weird, but we'll see why that works in a bit. Just here you'll be letting the particular integral be lambda sine, this time just an x, plus mu cos x. What if it was a cos 4x? Well then the particular integral would be lambda cos 4x plus mu sine 4x, or the other way around. It doesn't matter which order you put these in as long as you have both the cos and the sine. Whether it be sine or cos over here, you put both in for a particular integral. If you put a number here like a 5, it doesn't matter, it's the 4 that matters for the numbers here, the 5 is ignored, so I could put some numbers in front of here and it wouldn't change the particular integral you would use, it's the number in front of the x that matters. And you need both the sine and cos always, whether they're there or not on this side. The last kind of function you may see in FP2 is an exponential. It's very similar to the sine cos above. You can have exponentials like ex, or e of 2x, or e of minus 5x. And then the particular integrals you use will be lambda e of x, that one, or here it will be y is equal to lambda e of 2x, and here it will be y is equal to lambda e of minus 5x. So again, it's the number in front of the x that matters, that's what's got to be in there in your particular integral. Again, you could put a 2 here, a minus 3 here, a 5 here. It doesn't matter what number I put at the front, it's the number in front of the x that determines the particular integral. These may seem obvious. Usually people are happy with these three and this one. This one here seems always to cause a bit of confusion. Why have I got a cos and a sine when it's only a sine over here? It's all to do with the method. In a minute we're going to start differentiating these things and plugging them in here. And because when you differentiate sine you can get cos, and when you differentiate cos you can get sine, we need to include both these things here to give us enough sort of freedom to be able to pick a lambda and mu that work. But rather than me try to say it all very vaguely, let's do an example and see if that helps. Let's see if we can find the general solution of this differential equation, d2y dx squared minus dy dx minus 6y is equal to, and let's put the function of x as being sine of 3x. Now this is the same left-hand side as we saw in the other example. That's quite purposeful because it'll make our lives a little bit easier and save some time in this particular video. But this function here was 4x last time, now it's been changed to sine 3x. So let's see if we can solve this. The first thing we do is work out the complementary function. We do that by taking the same left-hand side, but writing it equal to 0. And we've done this in the last video, so let me skip ahead and write down the answer that we know from the last video. You can always go back and have a look at that beginning of that video again if you forgotten how to do that or think this is wrong. I don't know. That's the complementary function. Now let's do the second part, which is the particular integral. That's the bit we're really interested in today. And we've got to decide what we want our y to be. So we look over here and we think, okay, so it's sine of 3x, so I'm writing down lambda sine 3x plus mu cos 3x. And the first thing you do, just like last time, is we differentiate it. We're going to plug these things in here, so we're differentiating this. Differential of sine is cos, but we've got a times by differential of the bracket. Differential of cos is minus sine, again got a times by the differential of 3x, which is 3. Second differential time. Differential of cos is sine, well minus sine, times by the differential of the bracket. And the differential of sine is cos, times by the differential of the bracket. And we get that lovely mess there. Now we're going to plug these guys back into this left hand side up here. So the d2y dx squared is minus 9 lambda sine of 3x minus 9 mu cos of 3x. I'm going to wrap it in brackets just so we can see the terms more easily. Now I'm going to take away a dy dx, which is this bit. So minus 3 lambda cos 3x minus 3 mu sine 3x. And then we're going to take away a further 6 lots of this thing, the y part. So lambda sine 3x plus mu cos 3x. And we're going to put that equal to sine 3x. For the particular integral, it's actually equal to sine 3x. We're trying to find the particular y, which solves this equal to this. This is for the general function, or general solution at the end. Let's keep going. So let's collect the sine parts together and the cos parts together. So we've got minus 9 lambda sines there. Here we've got minus minus, we've got plus 3 mu sine 3x is there. And down here we've got minus 6 lambda sines. I'm doing that quite quickly. Feel free to expand these out first before you collect them together. I'm just saving myself a bit of time, a bit of space. The cos parts, we've got minus 9 mu's, we've got minus 3 lambdas, and we've got minus 6 mu's there, and that's all the cos 3x's. Probably should put a plus sign in there. I suppose that plus that is still equal to sine 3x. And now we can sort of compare one side to the other, try to write down some simultaneous equations in terms of lambda and mu. And we can see here that that's minus 15 mu plus, minus 15 lambda plus 3 mu is equal to 1, because the sine coefficient is 1. And this isn't over here, so this must be 0. So that means that minus 15 mu minus 3 lambda is 0. If we rearrange this, we get that lambda is equal to minus 5 mu. And we can use that to solve this equation, right? We plug that in there, we do the maths, and we work out that mu is equal to 1 over 78. We then plug that back into this formula, we find out that lambda is equal to minus 5 over 78, which gives us our particular integral as being minus 5 over 78 sine 3x plus 1 over 78 cos 3x. Okay, that last bit I just rushed through because it's just simultaneous equations. You can do that. It's this last bit here that's interesting.